Today we are going to start Chapter 7. Chapter 7 is about exponential and logarithmic functions. Specifically 7.1 is about exponential functions, growth and decay, talking about what those terms mean and what those graphs look like and what the equations that go along with those graphs also look like. An exponential function is a lot different than the other functions that we've dealt with. Last couple chapters we've talked about polynomial functions like x to the second, x to the third, where we see the x as the base and a numerical exponent. An exponential function means that the variable is actually going to become the exponent. So this is what the exponential function looks like. Y, or f of x, equals a times b raised to the x. And the key thing there is that that variable is now the exponent instead of being the base over here. To write out an exponential function, you really just need two things. You need an a and you need a b. The a is your representative of your initial amount. A lot of times in word problems, you're going to have some starting amount. That is what the a value represents. It also, in terms of a graph, is going to represent your y-intercept, and we're going to see that in the next slide. Your b value is your growth factor. That's really how much your a is changing every time that you go through some amount of x. So it's really what you're multiplying a by over and over again. That b value, the base, is the thing that's going to show the actual growth or the decay. If the b value is between 0 and 1, something like 0.5, 0.3, that is going to show decay. If that b value is greater than 1, it's going to show growth. And again, we're going to see when we actually graph these what it means to be decaying, what it means to be growing. So, to actually talk about being able to graph some exponential functions, to actually see what these look like, we're just going to start by going through and creating some tables. When we normally graph them, we don't need to worry about being able to create these tables. So we start off with plugging in the 0, 10 times 3 to the 0 power. What this means, when we see this here, order of operations, we have to simplify out the 3 to the 0 power. Exponents comes before the multiplication here. 3 to the 0 we know is 1. 1 times 10 is going to give us 10. We do the same thing for the 1. 3 to the first is 3 times 10 is 30. We do the same thing for the rest of these. We will get 90 and 270. When we get to the negative exponents, 10 times 3 to the negative first. We still need to simplify this down, but when we see that negative exponent, what a negative exponent does is it takes the base and is going to flip that base. The word that we're looking for here is reciprocal. We take what that base is, we find the reciprocal of it, which the reciprocal of 3 is 1/3, and we raise it to the positive exponent that we see. So it's going to 3 to the negative first becomes 1/3 raised to the positive first, which 1/3 to the first is 1/3 times 10 is going to be 10/3. We do the same thing for negative 2, so it's going to be 3 to the negative second, which means this is 1/3 to the positive second, so that's going to be 1/3 times 1/3, which is 1/9, times the 10 is going to be 10 over 9. Same thing for the negative 3, this will become 10 over 27. To be able to graph these, we can just go through and make a fairly nice x-axis because we have nice numbers here. The y-axis we're just going to have to be a little bit more lenient with. The first one and the important one that we place is this 0, 10. This is our y-intercept. So we could say this is approximately 10, place that value there. Then we go through, we can place the rest of these. Let's start off with the negatives. Negative 1 is 10/3, which it may help if we change this to a decimal, 3.3 repeating, which would be about there. This one is going to be 1.1 repeating, which is pretty close to the x-axis. This one here is 0.370 repeating, which is, again, very close to the x-axis. The 1, 2, and 3, the 1 is 30, which is going to be way up here. The 2 and the 3 we don't necessarily need to worry about because they're just going to get so extremely big off the graph. We draw this curve that goes through it. If we notice how it kind of curves this way, it's getting closer and closer to the x-axis, but it's not actually going to go through the x-axis, so we're just going to leave it like that, and that's what our exponential function looks like. Let's take a look at this other one. 10 times 0.5 to the x. We plug in the 0, and again, order of operations says we need to raise it to the 0 power first before we do the multiplication. 0.5 to the 0 is 1 times 10 is going to give us 10 again. We raise it to the first, so 0.5 to the first is 0.5 times 10 is 5. This will give us 2.5 and 1.25. We do the same thing for the negative 1. 10 times 0.5 raised to the negative first. So here's where we have to do the reciprocal of 0.5, which if you think 0.5 is really 1/2 to begin with, the reciprocal of that is going to be 2. So it's going to be 2 to the positive first, which is 2 times 10 So it's going to be 20, then 40, and then 80 when we plug the rest of those in. We make the XY table the exact same way. We can put the 10 here to say this is going to be our y-intercept, and then we just go through and place the rest of these. 1, 5, 2, 2.5, 3, 1.25. 1 negative 120, which will be up here, and we see that our curve is going the other direction. So there's our curve going the other way in comparison to this one. What we talked about on the last slide back here was if b is between 0 and 1, it shows decay. B is greater than 1, it shows exponential growth. Our b value was a 3. Since that's greater than 1, this is what exponential growth is. Exponential growth means as you look at this graph from left to right, and it's going to apply to the other one as well, is that as we look at this from left to right, our graph is going to grow, namely the y value. It's what happens to the y value to be able to describe that exponential growth and decays. How does y change? In this case, our y is getting a lot bigger. That's why it's a growth. Over here, our b value was 0.5, which is between the 0 and 1. That's why we have a decay. If we look at our y values as we're going from left to right, the y values are getting smaller and smaller. So that's why, again, it's a decay. Now, if you take a look at both of these graphs are going through the y-axis. They both go through at that 0, 10, which is the a value that we have out in front of what's being raised to the power. A is 10 here, A is 10 here. But the other thing that you may notice is that they're both getting closer and closer to the x-axis without actually going through the x-axis. When that happens, what we do is we call that x-axis an asymptote. Again, the way that we say that the p is silent, it's called an asymptote. What that means is the graph is going to get closer and closer to that line, but it's not actually going to go through that line. As a little bit of a disclaimer, there are graphs that will actually go through the asymptote, but for our purposes, what we're going to be working with this year, they won't actually go through that asymptote. So this line that we have here, the x-axis, is our asymptote. The way that we write out the x-axis is the x-axis is a horizontal line. And any horizontal line is always written out as y equals some number. And it's what point does that go through on the y-axis. This is the what point does that go through on the y-axis? It's the x-axis that we're trying to write out, which is the horizontal line, so it's going to be y equals something. And the point that the x-axis goes through the y-axis is right there at 0, so the equation of the x-axis is y equals 0. So our asymptote is y equals 0. An easy way to think about this for you Lord of the Ring fans out there is at one point in time Gandalf goes up against the Balrog, and Gandalf is basically the asymptote to Balrog. If you don't understand that, ask about it in class tomorrow. So let's talk about going through and graphing one of these. If we want to go through and graph this, let's take a look at this second one. We're going to leave this first one blank for a while. If we look at here, first thing we see is we have a number raised to the x power. As soon as you see that you have a number raised to the x power, that is going to represent your b value. So since we know b is 0.8, we can go through and already define it as a decay. But if we want to talk about the a value, because we need to know the a value should be right here. Since we don't see an actual a value, the number that we're going to put in is a 1. And that's going to help us in terms of being able to sketch the graph. When you sketch the graph, you have to show two things. The first one that you have to show is that y-intercept. So we're going to put this to say this is the value of 1, and our graph is going to go through that. Then we have to show a decay, which from what we said before, that means as you're going from left to right, the graph is going to be decreasing. So from left to right, the graph is decreasing. But as it gets closer and closer to that x-axis, it's not actually going to go through the x-axis. And when we sketch the graph here, we do not want to show that this is going through the x-axis. That's a key part of an exponential function, the y-intercept, and then showing that we have an asymptote on that x-axis. The way that we show that is that it's not going through that x-axis. Part 3, labeling the y-intercept. Well, we've already labeled the y-intercept in our sketch. We don't need to worry about that. The asymptote, which we said was the x-axis. Again, the x-axis is a horizontal line, so we just have to write out the equation of that horizontal line. Any horizontal line equation is going to be y equals. Well, what part of the y-axis does that go through? It goes through 0 on the y, so our horizontal line is y equals 0. That's our asymptote. Our domain and range. Domain and range are talking about, first off, domain is talking about what x values can this graph reach, which when we take a look at this, it's what are the possible x values that we can use for x when we put it into this equation. Well, if we take a look at this graph, we could see that it's going to go to the left because it's going up, but at the same time that it's going up, it's also going out. So it's going to reach negative infinity at some point. As it goes to the right, it's going to keep on going to the right, which means that it's going to reach positive infinity. So there's no spot on the x-axis that this graph cannot reach, no x value that we cannot use. The way that we're going to write that out then, since we can use every possible x value, is our domain is just going to be all real numbers. Our range, on the other hand, our range, what we're looking at is what possible y values can we get out of this equation, as in what possible y values can this graph reach. Well, we know that the graph is going up, so as it keeps going up, it's going to reach a positive infinity. But as the graph is going down, it's not going to go all the way down. It's only going to reach towards the x-axis. It's not going to hit the x-axis, but the value that it's going to go towards is 0. So it's really going to cover every value from 0 up to positive infinity, but we can't include that 0. So we can say that the graph is going to get close to 0, and it's going to go up to positive infinity, continually going up, so our y values are going to be greater than 0. Now, a lot of times what people like to do is they like to write out our domain and range in set builder notation. And the way that we use set builder notation is we take an inequality that we have here, which is inequality that we already wrote, and we just add some brackets around it. We're going to put a bracket at the end to say that we're ending, a bracket at the beginning, and then we're going to say y with this horizontal line here to represent this inequality that we have. What this means is these brackets are talking about a set, as in a group of numbers. This y is just saying that we're dealing with values of y. We don't know what those values of y are, but this line is going to tell us that we are going to define these values of y as y is greater than 0. The way that we read this is those brackets are talking about the set of. The y is just going to be all y's. This horizontal line here means such that, and then the inequality just means the inequality, such that y is greater than 0. And this is set builder notation. You guys are going to be using this a lot in FST and pre-calc. This other one, I want you guys to take a couple minutes, now or either at the end, and I want you to do this one for class tomorrow. So this is going to be a homework problem for tomorrow, is to be able to do the same thing for this one as what we did for this one. Before we actually get into the word problems, we're going to talk about how word problems are written. They don't actually tell us what that growth factor is. We have to figure out what that growth factor is. A lot of word problems are going to use words such as increase or decrease by some percent, as in each time this value changes, it's going to change by some percentage of the value that it's currently at. So what we want to do is, instead of saying it increases or decreases by some amount, we want to figure out what that actual growth factor is. Think about if you go to a store and you buy something that has sales tax. All right, what you're going to do is to figure out your total price for the sales tax. Let's say we have a 7% sales tax. We use this one here. That sales tax is going to increase that amount. Well, to figure out what that sales tax is, you have to multiply that by 0.07. Now, let's say we don't actually know what that number is, so we're going to call it X. We take that price that we have, we multiply it by 0.07. But once you get that sales tax, you're going to actually have to add that to the original price to get the total. Well, 0.07x plus x, which this is like 1x, would give you a total of 1.07x. And that's going to be the total price that you're going to get in one step. Instead of saying let's multiply by 0.07 and then add it to the original, we can just multiply by 1.07. Another way to think about that is when it uses the word increases by 7%, think increase means plus. I have to add to that 7%. Well, what am I adding 7% to? I need some other percentage to add 7% to, so it's going to be 100%. And 100% plus 7% is 107%, which is 1.07. And that's the number that we're going to use as the growth factor for that problem. If it's a decrease problem, as in decreases by 12%, you can do that same thing. Decrease means minus 12% with 12%. What are we subtracting 12% from? That would be 100%. which would give us 88%, or 0.88 as a growth factor. So let's actually take a look at a word problem. Tony purchased a rare 1959 Gibson Les Paul guitar in 2000 for $12,000. Experts estimate that its value will increase by 14% per year. Use a graph to find when the value of the guitar will be $60,000. So since it gives us this information here that it's increasing by 14% each year, implying that it's not going to be the same amount that it increases by, because 14% of 12,000 is different than 14% of 60,000 at some point in time. This is going to be an exponential function, as in y equals a times b to the x. Remember, the a value is the initial amount. So in this case, the initial amount is what he purchased it for, which was 12,000. So it's going to be y equals 12,000 multiplied by b, which is our growth factor. So we need to figure out our growth factor. The percentage is going to give us our growth factor. It's 14%. It's increasing, so we're going to say we're adding 14% each time. But what are we adding 14% to? That's 100%. So it's 114% is what we're actually going to use. And that number that we put in here is the decimal equivalent, 1.14 raised to the x. So there is our exponential equation that we are going to use. Now, all we have to do is answer the question, which it says, when will it be $60,000? What we want to know is what variable is actually going to be equal to $60,000. What variable is going to be $60,000? Normally, x deals with time. Since we're talking about years here, he bought it in 2000, so x is time. So what variable is it? That variable needs to be y. Now, what you may think is we're going to take this y and we're going to plug this y in to this equation here and say that it's going to be 60,000 equals 12,000 times 1.14 raised to the x. We get rid of that 12,000 by dividing by it, and we get 5 equals 1.14 raised to the x. The problem is we can't just go through here and divide by 1.14 to get the x by itself, because this x is not being multiplied by that 1.14, it's being raised to it. So right now we do not have a way to actually solve that 1.14 raised to x. We don't know how to get the x by itself. We will in a little bit of time, but we don't know right now. So we have to go back to the drawing board and talk about how we can solve this. Well, we have this equation that says y equals 60,000 and another equation that's y equals this. This, being just y equals something, is a horizontal line, and the other one is an exponential function. So what we can do is we can actually go through and graph these two lines. Now, when we talk about being able to graph them or graph these two equations, this being an exponential function is going to have something that's going to go through and it's going to look like this. This one being a horizontal line is going to go through and look like this, and really to find out what that x values be where these two are equal is going to be that spot right there. All we have to do is talk about how to actually graph these, as in where are we going to find that intersection at. If you take a look, remember this is your a value, so this is really your y-intercept. You're going to have a y-intercept of 12,000, and this one being a horizontal line at 60,000 means that it's going across here at 60,000. So what we want to do is we need to make our y value of our window, our y max value, higher than 60,000. Since we know that's going across at 60,000, maybe we want to make it 70,000 so that we have enough of a big enough window to actually see where it's going to cross. And then we can go through and try some different x's. But think about this. The x's, if it's 12,000 and it's increasing by 14% each year, it shouldn't take too many years to actually reach that 60,000 mark, to be 5 times as expensive. So we don't need to make our x's too big. We don't need to sit there and make our x max like 300 or 400, because it's not going to take that many years for it to be 60,000. So what we can do is we can make our x's a little bit bigger, 20, just to try to get a better representation of where this would be. If that's not enough, we just need to make our x max a little bit bigger. And when we go through and we find where those two cross, we just have to find the intersection point, which the calculator is going to help us with this. To find that intersection point, remember this is where we use the calculator's second trace, and under second trace we are going to select intersect. And when we do the intersect, it's going to ask us first curve, second curve, guess. We run through all that, and it should give us an intersection point that says x equals 12.28, y equals 60,000, which that's the amount that we were looking for, which means this is going to be the number, the amount of time that it's going to take, which we were talking about it It just said 2000. We're talking about years, so it's going to be 12.28 years to be able to get a value of 60,000. 12.28 years means sometime in 2012, but since at the beginning of 2012, since we're just talking about specifically years, at the beginning of 2012, it's not quite going to be 60,000. So if we had to estimate then, we would really say it's 2013. This, though, is a better answer because we're talking about an exact answer. If it's asking specifically what year, we'd want to say 2013. But if it's not saying specifically what year, we can just say how much time would it take to be 60,000, which is 12.28 years. We have one more question that we're going to take a look at, but what I want you guys to do is I want you to do this one for homework as well. I want you to go through and write out the equations and see if you can graph it. If you have a graphing calculator, go through and graph it. If you don't, I want you to write out the equations and I want you to sketch a graph of what this would look like. This time, though, it says decrease, so you have to be careful. That's going to be the opposite of what we did in the last one. Again, if you don't have a graphing calculator, write out the two equations that you would use and sketch a graph and then circle where those two curves would intersect.